dear students, I welcome you back to the lecture 4 of electrochemistry. In the previous lecture, we have seen what is electrode potential, what is oxidation potential, what is reduction potential. In this lecture, we will be seeing what is the relationship between oxidation potential and reduction potential. We also will be seeing what is EMF of the cell and will solve some numericals on that. So before beginning with the new lecture, I want to revise from the previous lecture. So this is your typical Daniell cell, which you have already studied. You know that the left part of this cell is called as oxidation half cell and the right side it is called as reduction half cell. The reason is on the left side there is oxidation reaction which is happening and on the right side there is reduction reaction which is happening. The potential which is measured on the oxidation half cell is called as oxidation potential. And the potential which is measured at reduction half cell is called as reduction potential, which can be written as oxidation potential can be written as E of Mn plus. And this side, reduction potential can be written as E, M, N plus and M. This is just an oxidation reaction which is represented like this. The oxidation number increases from 0 to N plus. It can be 1 plus, 2 plus, 3 plus, whatever it is. And similarly here, the oxidation number decreases from N plus to 0. So this is an oxidation reaction. This is a reduction reaction. Potential measured is called as oxidation potential. Potential measured is called as reduction potential. Students, for this reaction in Daniell cell, the oxidation potential measured was plus 0.76 volt. And for this reduction reaction of the Daniell cell, the reduction potential measured was minus 0.76 volts. What do you understand by this? You know that the entire electrochemical cell is under electrical neutrality. If the oxidation potential has a plus sign, then the reduction potential must have a minus sign. So now you have to remember one thing. Note, for any half cell, its oxidation potential and reduction potential both can be measured. Understand this particular note very carefully. What they are saying is, for any half cell, it can be oxidation half cell or reduction half cell, you can calculate both oxidation potential and reduction potential for either of these cells. I mean to say, this is an oxidation reaction and its oxidation potential is 0.76. Now, for this particular reaction, reduction potential also can be calculated. The only problem is then the half cell becomes non-spontaneous. Understand? This is a spontaneous reaction. This is a spontaneous reaction. If I wish this reaction can be reversed, then how the reaction will look? Zn2 plus 2 electrons gives Zns. Now you may ask me, ma'am, how is this reaction possible when the oxidation reaction is like this? Students, now this is no more oxidation reaction. This is a reduction reaction because electrons are being accepted by Zn2+. And this reaction is possible, but it becomes non-spontaneous now. And for this reaction, reduction potential also can be calculated, but in a reverse sign. Are you following? So for this half cell, you can calculate oxidation potential also. You can calculate the reduction potential also. Similarly, this side, you just copy this. I will erase and explain only the reduction half cell now. Okay. Now, students, this is a reduction half cell and this is a reduction reaction. Therefore, the reduction potential measured is this much. Now, my question is, can this reaction be reversed? Yes. Copper metal can lose 2 electrons to become copper 2+ state. This is possible, but it will be non-spontaneous reaction. And this reaction is an oxidation reaction. Therefore, its oxidation potential also can be measured, which is 0.76 volts. So, in general, whether it can be oxidation reaction or reduction reaction, they can be reversed. For this cell, oxidation reaction also can be written, reduction reaction also can be written. And for this side, the oxidation reaction also can be written and reduction reaction both can be written. Is it clear? Okay. Now, what is the relationship between oxidation potential and reduction potential? Oxidation potential is always having a reverse sign of reduction potential. If oxidation potential is, say, 0.76 volts, then its reduction potential will be minus 0.76 volts. If the reduction potential is minus 0.76 volts, then its oxidation potential can be written as plus 0.76 volts. So this is the relationship. If you are taking standard oxidation potential and standard reduction potential, then this will be the relationship. Standard oxidation potential is equals to minus of standard reduction potential. Is it clear? Okay. Okay, so now what is EMF of this cell? So now EMF of the cell is designated as E cell. And the standard EMF of the cell can be designated as E naught of cell. So students, EMF of this cell can be given as reduction potential at cathode minus reduction potential at anode, or reduction potential at right hand side or right half cell minus reduction potential at left half cell. So what is EMF of the cell? How it can be calculated? It is nothing but reduction potential at cathode side minus reduction potential measured at anode side, or reduction potential measured at right half cell minus reduction potential measured at left half cell. If you observe carefully, right half cell itself is a cathode and left half cell itself is anode. Students, this may take little time to understand. As you see the numericals, you will get to know it very easily. Okay. So this is EMF of the cell. If the same standard EMF of the cell is asked, then it will be E naught of cell, and here also it will be E naught of cell. Okay. So now we will be seeing the numericals, and then you will come to know why we have taken only reduction potential. Students, it's very much clear. Now you may ask me a question that, Madam, at the anode oxidation potential is measured. Why have you written reduction potential? You have to remember that in the note I had written, for any half cell, its oxidation potential and reduction potential both can be measured. And IUPAC says that you always consider reduction potential only and don't consider oxidation potential. That is why we have taken only the reduction potentials. Okay. We'll see some numericals. Numericals on EMF of the cell. So before that, I'll just write all the formulas. That is, OP is equals to minus RP, or SOP is equals to minus SRP. EMF of the cell equals to reduction potential at cathode minus reduction potential at anode, or reduction potential at right side minus reduction potential at left side. Standard EMF of the cell can be written as standard reduction potential measured at cathode minus standard reduction potential measured at anode, or standard reduction potential measured at right side minus standard reduction potential measured at left side. So these are the formulas which are going to help. Most importantly, this. Okay. First numerical. Find standard cell potential. Standard cell potential, that is E naught of cell, EMF of the cell, given Ni to Ni2 plus salt bridge. This is having 1 molar concentration. Then we have Ag plus 2 Ag. Again, this is having 1 molar concentration. Given E naught of Ni2 plus Ni minus 2.5 volts and E naught of Ag plus 2 Ag given plus 0.80 volts. Okay, this entire is a question. What they have asked is, find the standard cell potential. Standard cell potential is nothing but standard EMF of this cell. And they have given one cell representation. Okay, this is how we have learnt in the cell representation. Left side is oxidation, right side is reduction. See there, oxidation number has increased from 0 to 2. It means it is oxidation. Oxidation number has reduced from +1 to 0. It means it is reduction. So this is the cell and separated by a salt bridge. They have also given some data here. Ni2 plus to Ni, the potential measured is this much. First observe it carefully. Is it oxidation or reduction? It is reduction here, isn't it? 2 plus 2, 0. It is a reduction. Therefore, this potential is reduction potential for this reaction. Observe this now. +1 to 0. This is also reduction and this is also reduction potential. Now, EMF of cell, standard EMF of the cell says standard reduction potential at cathode minus standard reduction potential at anode, isn't it? Now, who is at the cathode? Cathode is this, isn't it? And who is anode? This. Reduction potential of cathode is given here. Reduction potential of cathode is given here. How much is that? 0.80. Observe carefully. Reduction potential of cathode. How much is that? Plus 0.80 volts. Minus standard reduction potential of anode. Reduction potential of anode. This reaction is anode. So how much it will be? Minus of 0.25 volt. So what would be the answer? 1.05 volt is the cell potential of this cell. Okay. Now I'll clear one doubt of yours. Here it is oxidation, here it is reduction. Okay. So now this is a cell reaction. This is oxidation, this is reduction. Fine. That is absolutely correct. But here, instead of giving the oxidation reaction, they have reversed the reaction and given the reduction potential. I told you, for this reaction you can write the oxidation reaction also and reduction reaction also. And they have given the reduction reaction and the reduction potential. Because in the formula, we require the reduction potential. Okay? One more numerical. Find standard cell potential of given cell Zn, Zn2 plus 1 molar, Pb2 plus 1 molar and Pb. Okay. Given, they have also given some data. Given E0 of Zn to Zn2 plus. Given 0.76 volt plus. E0 of Pb to Pb2 plus. That is 0.13 volts plus. Okay. Solution. So we know what is EMF of this cell. Standard EMF of this cell is nothing but standard reduction potential at cathode minus standard reduction potential at anode. Zn from 0 to +2 state is going. So this is your oxidation. Oxidation happens at anode. Reduction in the oxidation number from 2 + to 0 is a reduction reaction, and this reaction happens at cathode. We know it already. Okay. Now the formula demands us reduction potential, not the oxidation potential. And for that they have given some data. Observe here. Zn from 0 to state, 0 state to 2 plus state, oxidation reaction, and the potential is oxidation potential. But do we require oxidation potential? No. We require reduction potential. And I had told you, oxidation potential is minus of reduction potential. Therefore, this oxidation potential, this is oxidation reaction. This is oxidation potential. We have to convert it in the reduction potential, which will be minus 0.76 volts now. Similarly, here also, 0 to 2 plus state, it is oxidation. The potential measured is oxidation potential. But we require reduction potential. So it can be written as minus of 0.13 volts. Okay. So now, reduction potential at cathode. Who is at cathode? This or this? It is this which is at cathode, isn't it? And its reduction potential we have converted to minus 0.13 volts. So it will be minus 0.13 volts minus, who is there at anode? Obviously this is there at anode. And its reduction potential we have measured is, we have converted is minus of 0.76 volts. So the answer would be 0.63 volts. This is the way you have to convert oxidation potential to reduction potential. Because in the formula, we require only the reduction potential and not the oxidation potential. Thank you.